Alright, when we left off earlier, we're talking about the motor torque, how we find our torque. You have those 4 questions that I send. There's other things that we're going to work alongside, but the first part for today, well, on Tuesday, was finding the torque of those 4 motors that I send in the assignment. Next would be the, let me go here, and it says NEMA torque classification. The NEMA classification motor based on their torque characteristics. The minimal starting torque motors are classified as class A through F. Each class has a different range starting torque, for example. Class B, the most common class of motors, are as a starting torque that is 150% of the full load torque. Some examples of the things are on table. Let me see if I have it on here. No, they don't. So on page 190, down at the bottom, figure 13.7, it says a single phase AC motor, and then it says a percentage of the full load, and then it has a three-phase AC motor and a direct current motor. So it has a different percentage of the full load current when it starts. Okay, so the full load torque when it starts. And you can see them 400%, 400 to 500%, low and high. 400 low, 500 high. So it's 400% to 500% when it's the initial start, because that force that it has to take. And this is where we're going to the lock rotor, the indicating codes. So if you notice on the sheets that I sent, there's a code on each one, except one. And that was, hopefully you catch it. And we'll get to that in a bit. Selecting the motor. Motor determine which type of motor is used. Particular installation is an interesting challenge to make the proper motor selection. Several general factors are considered. So here are these. So it's the power, the load, the environment, and the temperature. So where's this motor going? One is, what's the applied voltage present? What do we have present? I mean, we have 12240 single phase, 12208 three phase, 277 480 three phase. So what is our voltage present? And that's our first one. So it says power source. Most motors are either single phase, alternating current, three phase, or direct current source. In some instances, either AC or DC can be used. Normally, the available power source dictates the motor type. For each type of service, there are a variety of motors available. So on the power source, when I was at the slaughterhouse, we had a machine that was a slicer that we got. But the problem was, on the AC side, that slicer, the RPMs were too slow. The RPMs were too slow. So I got up. I got to work early one morning. Called up the manufacturer in Germany. Unfortunately, the book that we had was in German. They didn't send us one in English. So I called up Germany, and I was able to get one of their engineers, and we talked to what can we do, because it was slicing too slow and it was making too many nicks that they weren't passing inspection. So a lot of the meat that was being sliced ended up going back to get redone. Anyway, so he told us the best thing to do is to change that AC motor to the DC motor. That we can kick up the RPMs to 4,000 to 5,000 RPMs. Or he says we could double, maybe even a little bit more. So we put in a rectifier, used an AC motor. All we did was just rectify the current, and then we changed it to DC going to the motor, which the motor would run either way, and it ran. And obviously the speed went up real fast. So we used a rectifier to rectify the AC motor to a DC motor. Load. A motor usually like any machine, accomplishes a task. For a motor to perform the task efficiently and dependently, it must be properly matched to the load. If the motor is too large, too small, it will not perform economically. So the load, what kind of work is it going to do? You know, we used to have guys, motor go bad, and they go out and change the motor. Well, they go out and look at what they had in stock, and a 10 horsepower motor blew up. So, but they had the same frame number for a 15 horsepower. So all of a sudden they put the 15 horsepower in, and all of a sudden the motor wouldn't work. Why? Well, everything that was on it, the protection, the wire, and everything else was sized for a 10 horsepower motor. So they were having problems. We had to go back and redo everything, and then they started noticing that their efficiency wasn't the same. Okay, so now they got a bigger motor, but they didn't need it. Okay. The environment, that's very easy to say. The location can affect motor selection. Some motors are most durable than others. Moisture, dust, explosive gases, corrosive chemicals, radiation, temperature extremes, and vibration can be harmful to motors. So again, where's this motor going? What type of motor is it? In the same slaughterhouse we had one, the machine kept blowing up. And we kept telling the guy, and I said, hey, get us an encapsulated one so we can put it on. No, that one costs too much money. So he was just buying this $125 motor that we kept changing out every 3 months, because it would go bad due to the watering down of everything. So eventually something would break down, the motor would go bad, and then we have to change it out. In order to change that one motor out, we had to take the other motors to get to that one. So I think it would have been better to spend the $2,000 for the encapsulated motor compared to the $125 motor, because now when machine's down, you got 5 people that are standing around doing nothing for 4 hours till we get these motors changed and aligned, because it had 4 motors. It was like a conveyor belt type thing. So it takes about 4 hours to do it. So if it's outside, it's got to be able to handle the environments. If it's in a gas with explosive vapors, okay, well, the last thing you want is a motor. I don't know if anybody has noticed, when you turn a fan on, so every once in a while you have that spark. Well, if you have gases in the air, the last thing you want to see is that spark. And temperature extremes. I told you all the story that while I was working in, we had an area they put in some new equipment, and it took the temperature up to about 130 degrees. All of a sudden, these older 130, 140 degrees. Well, a lot of it was wired in TW. A lot of that TW started to fail. One is the ambient temperature of the room, and then these motors were getting hot. So these motors were also, they weren't designed to be in this high temperature. So the motors started to fail, so we had to change the motors out. So we changed the wiring, we changed the motors to have a higher ambient temperature, and then we put some fans and stuff to try to control the heat, exhaust fan to exhaust the heat, and we put some vents to supply cool air. But that wasn't added till after we spent 4 weeks in there sweating our butts off in 130 degrees. And again, the environment, I was talking about the heat. So overheating is the largest cause of motor failure. High temperatures areas do not allow the heat generated within the motor to dissipate. The most common ambient temperature limit is 104 degrees Fahrenheit or 40 degrees C. The ambient temperature limit is shown on the motor or the nameplates. When you look at most nameplates, it would have that ambient temperature 40 degrees C. And we'll get to that when we start talking about service factor, because that's where that comes in. On one of them I put the ambient instead of the service factor. Not all of them, I didn't put the NEMA code letter, the NEMA letter, I didn't put it in, because all 4 of them were B, and like it said in the book, that is the most common type. That is the most common type. Okay, motor enclosures. Motors can be classified as either open or enclosed. Yep, hold on. Motors can be classified as either open or enclosed. An open motor allows air to flow freely through the enclosure. In an enclosed motor, the enclosure seals the motor from surrounding air. Within the general classification of open or enclosed, there are a variety of enclosure types available. Many factors affect motor enclosure selection, and following are some of the most important. Environment. So here they got the environment, supplied equipment, and availability. Just as the area the motor is installed will most likely dictate the type of enclosure needed. Hazardous location require explosion-proof enclosures. Areas where liquid may be present require a drip-proof or splash-proof enclosure. Supplied equipment. A protective enclosure may be supplied for the motor supplying power to critical equipment, even if the enclosure is not required based on the environment. And availability. A given size and type of motor may be available within a certain enclosure types. So again, it comes into different what's available so you can use for what you have. On the supplied equipment, you know, it comes within the cabinet already to protect the motor itself. I don't think they have it on here. Oh yes, they do. So the motor, different motor enclosures. Up here they have, let me just put the book down real quick. So we have the drip-proof design for water and fluids falling at an angle at 15 degrees. Splash-proof design so water and fluids falling at an angle up to 100 degrees from vertical cannot enter the motor. Guarding. Openings that allows access to rotate and energized parts are protected to prevent passage of any object as large as 3/4 of an inch. A rod. Semi-guarded. Some openings are guarded while others are left open. Normally the openings of the upper part externally ventilated. And then you have the enclosed, the water-cooled, pipe-vented, fan-cooled, non-vented, explosion-proof, or dust ignition-proof. The only reason I kept telling them that we wanted an enclosed, a encapsulated motor was when they go in there and they were washing these things down, they just got water. So you can't, if it's going to be pointed in either direction where the motor was at. So we wanted to make sure it wouldn't get in. So that would fall under that splash-proof design so water fluids are falling at an angle up to 100 degrees from vertical cannot enter the motor. So again, we didn't want water getting in because we didn't know which way it was going to go in. Okay, motor letter code. Section 437B identifies code letters used to indicate the motor input with lock rotor. This is the indication of the current drawn by the motor when it starts. The starting current is much larger than the current needed once the motor is running. Says table 437B, which is this one here. So this is another part that we're going to do with that assignment that I handed you out. So you're going to find that code letter. Okay, on one of them it doesn't have code letter, and I'll explain it because I don't want nobody getting confused. And that's the way the nameplate came. That's the way the nameplate came. So that's where I wrote it down to give it to you as an example. So it says KVA. And I think that was on the 200 horsepower motor. So it said KVA. Instead of saying code letter or code, it said KVA. So and then it had a letter right next to it. So this is what the starting, when a motor starts, we have the minimal and the maximum. We have the minimal and the maximum. And they got an example on 13.2. So they're giving us a 25 horsepower. And 240 volt three-phase. Okay, the other video I was talking about the 122, 120, 208, 277, 40. There is also the 240, 122, 40, three-phase, 122, 40, three-phase. That's the one that's got that high leg where B phase is 208 volts, A phase is 120, B phase is 120. If I go from neutral or grounding, from the grounded wire or the grounding wire to B phase, it's 208 volts. So you always have to be careful with this one. You'll find it a lot in some industrial areas. You won't find it in residential areas, but you'll find it in industrial areas. So the other saying has got code letter F. So all they do is get this horsepower, 25 horsepower, and then multiply it, code F, come down here, it's 5.0, multiplied by 5, kVA equals 125 kVA. And then we get the high part is 5.9. 25 times 5.9 kVA equals 139.175 kVA. No, 0.75, I'm sorry. 0.75. Okay. Next is we're going to divide it by the voltage. Okay, so right now, kVA, this is watts. This is watts. So we know the voltage, we know the watts of the motor. Now we have to find the amps. So I equals P divided by E. So we get the first one. This is 125,000 divided by 240 times 1.732. Okay, in the book they're telling you to do this on the side and then divide it. I don't do it that way. I'll just put it under here. And then I'll get the next one is 139,075. And again, 240 times 1.732. That was a three-phase, right? So again, remember, these are bottom number dividers. These are bottom number dividers. So, get my calculator here. I know it's in the book, but 125, it works better when you turn it on. 125,000. Divide. Okay, these are bottom number dividers, so I hit divide, 240. Hit divide again, 1.732 equals 300.7 amps. And we'll do the next one. 139,750 divide 240 divide 1.732. Oops. I hit the wrong number there. 139,750 divide 240 divide 1.732 equals 336.2 amps. Okay. How to get that 1.732? Square root of 3. 1.732. Now on your calculator, hit 3, hit square root, and there's that 1.732. Okay? This is the starting torque of a motor. So when that motor turns out, it's up to 300 amps. Okay? Up to 300 amps. Let me look at mine. Because I don't have an amperage, I would look at my code to find out more or less what the amperage is on this. So that'd be the 43250. At 230 volts, 25 horsepower. So basically this is about a 68 amp. This is about a 68 amp motor. This is about a 68 amp motor. When it starts at the low end, it's about 300 amps. At the high end, 336. And that's what this coat letter does. This is what this coat letter does to do our starting amperage, because that torque, remember, when that torque, if it's at 150%, it's starting at 150% above its rated torque when it turns on. Okay, what does it do to the amperage? You can see right here, it went from 68 up to 300 just when it turns on. So when we start doing this, that's when people are always like, well, why do you size a breaker 300%? Or 250%, I'm sorry. A breaker is 250%. A time delay fuse is 175%. Fast blow, or a one-time or single blow, or whatever you want to call it, a regular fuse is 300%. And then there's also the instantaneous trip, which is 800%. Okay, me and my 40 plus years of in the trade, I've never installed an instantaneous trip breaker. I've never installed an instantaneous trip breaker. Okay, so your letter codes, here they're just talking about the indicator motor input lock rotor. So your lock rotor indicating code, so it has, they all have a letter on them. And it would either be under code letter or KVA. Okay, KVA. So that's why I did it the way I did it in the assignment that I sent out, so you could see this. So you could see this in case it ever happens out in the field. Service factor of motor's ability to withstand minor overloads shown on the nameplate. On the ones that I sent you, it does have the nameplates. Hold on a minute. Trying to find it here. So again, this starts on 43032, which is in the code book is on page 304. And it says more than 1 horsepower each motor used in a continuous duty application rated more than 1 amp shall be protected against overload by one of the following means. So an overload, we size that overload by the service factor. Okay, we have an overcurrent protection device. It's not an overcurrent protection, it's a short circuit protection, because it's either at 175, 250, or 300% of the rated of the motor. Why? Because when the motor turns on, it has to be able to get up to here. When the motor turns on, it's going to have to get up to here. So if I got a 15 amp motor and I put a 20 amp breaker in, and it gets up 4 or 5 times higher, so it gets up to 50, 60 amps, what's going to happen to the 20 amp breaker? It's going to trip, it's never going to start. So we put in these thermal protectors. Thermal protectors are called overloads. Out in the field, heaters. So the little heaters that we put on them, they're on the starters that when we're doing electrician 2, in the residential part, talking about motors, and I talked about them. So again, this is article 43032 on page 304. Separate overload device. A separate overload device that is responsive to the motor current. This device shall be selected to trip and shall be rated no more than the following percentage of the motor nameplate full load current rating. So it says motors with a marked service factor of 1.15 or greater use, I got it in my thing. it's got a service factor at 1.15 or greater, use 125%. If it's marked 40 degree C or less, use 125%. And all other motors are at 115%. So when you're going to look at the nameplate, this is what you're going to find, and you're going to look. Okay, a lot of times you may find a motor that says 40 degrees C, but the service factor is 1.0. Okay, so the service factor is 1.0. Okay, that means that motor can run at 100%. Well, and that's a motor built to withstand minor overloads. Well, if it's got a service factor of 1, if it has a service factor of 1, we don't want it to get up too high. So that's why it's at 115%. So the ampacity, if it starts to get hotter than 100%, this overload picks up the heat and then trips out. This overload picks up the heat and trips out. And the code further on goes to say on number 2 here, it's a thermal protection integrated with a motor approved for use with the motor and protects on the basis that it will prevent dangerous overheating of the motor due to overload and failure to start. The ultimate trip current of the terminally protected motor shall not exceed the following percentages of the full load current given on tables 430, 248, 249, and 250. So it says motor loads current 9 amps or less, 170%. Motors current with 9.1 to 20, 156. All other motors greater than 20 amps at 140%. So there's where it goes. And then it goes on further down, and you go to same page. I'm on page 305 of the code. And then you go on, it says section C. It says section of overloads where the sensing element or setting of the sizing of the overload device selected in accordance with 430.32A1, 432B1, 430.32B1 is not sufficient to start the motor or to carry the load. Higher sensing elements or increment settings or sizing shall be permitted to be used, provided that the trip current of the overload device does not exceed the following percentage. So again, 1.15 or greater, 140%, 40 degrees C or less, 140%. All other motors is 30%. So it's allowing to go up an extra 15%. So let's say you go in there, I got a service factor of 1.15 and you use this. And the motor, as the motor, and it trips out. And it trips out. The overload strip out, not the breaker. The overload strip out. Then you can go up there and take it at 130% for your service factor. But only after it doesn't allow the motor to start. Only after it doesn't allow the motor to start. Okay, so you have your next assignment is to find your service factor. How's service factor? You can see it says SF. Okay, on one of them I didn't put the service factor because I put the ambient temperature. Okay, so didn't have the service factor, so I used the ambient. Again, I'm giving you everything so we can find it. And it says, what is the maximum output of a motor rated 30 horsepower with a service factor of 1.25? The maximum horsepower is rated. So the example they got here, what they're using is they're using a 30 horsepower motor, so they got the 30 horsepower. Okay, they multiplied by 125%. Because this one has a service factor of 1.25, so they multiplied it, and they're using 37.5 horsepower. Okay, so the service factor, if you multiply the service factor times the motor, that's what it's allowed in horsepower to go up, according to what the book is going. I'm showing you what the book says. I'm also showing you how we find the thermal overload protection using the service factor. So it's two different things. One motor's talking about one thing, I'm talking about another. The book's talking about the horsepower. So if you got a motor that is a service factor of 1, so that motor, if it's a service factor of 1, 30 times 1 is 30. That's it. So it can't run above it. So we have to protect that motor so it doesn't get above it. Okay, same thing with the others. So if you have a motor that's 1.15, you can multiply it, and that'll give you what it's going to run above. It can run above, so it allows minimal overloads. Alright, so I'm going to drop it here before I get into any other. And again, now, first I gave you torque. Now I'm giving you service factor using the service factors. You have the number, you have the codes. I gave you the codes, what page you're on, and again, they're right here. 1.15 or greater, 125%. Mark 40 degrees C or less, 125%. All other motors at 115%. We're not going to do the horsepower the way the book shows it. We're going to do the horsepower using the thermal. We can do it both ways, I'm sorry. We'll do it both ways. So one is the horsepower, the way the example 13.3 does, and then we're going to use it to find the ampacity. Okay? So because you don't have a code book, you don't have the you do have the ampacity of the motors. So you look at the ampacity of the motor, use that because I send it in. So you have some are 120, or 240, 460. Do it on both. Okay, do it on both. So if I had it at 240 volts, 230 volts, what would be the thermal rating? Or at 460 volts, what is the thermal rating? So you have, two of them were dual voltage and 2 of them were single voltage. So again, I want to see on the dual voltage, both voltages at the 230 volt and the 460 volt. And then on the single voltage, well, only the single voltage. Okay? And then you can do it this one also, but again, you want to do this, multiply on the amperage, and the horsepower. So the way the example is, and then we're going to get the amperage of the motor, multiply it by, depending where your motor ends. Alright, if you have any questions, email me. If you don't understand something, email me, let me know, so I can explain, okay? Or maybe if enough people are confused, and then I can put another one. Remember, I'm short on time because this camera only does 29 minutes at a time. Alright? Y'all have a good one. To the next video.